Hi everyone, hope you have a great day today and you had a wonderful Thanksgiving. Hope that break was long enough. So we have, let's see, 2 more weeks until this semester is over. And we're going to have to cover 12.4 today, and we'll see if we finish 12.5. Or else we'll finish it on Thursday. And then your fourth exam will be due this Sunday on the 6th. And your final will start on the 10th, and you will have until Sunday, the 13th at midnight to finish the final. Okay? Amy, you have any question or concerns about the fourth exam or final?
Professor, I was wondering if you're going to share the PowerPoint for these next two lectures. It wasn't on our Blackboard yet.
Oh, is it? Okay, I'll upload that right now.
Thank you.
Alrighty, it is up now in the content folder.
Okay,
Okay. Counting theories is fairly easy, and same thing with binomial theorem. It's basically just formulas. So there are 3 total formulas that you should memorize for this section and the next one. So let's get to it. Okay, so chapter 12.4 is about counting theory. So this is basically learning how to deal with permutation and combinations and be able to um, calculate the probability that something will happen. Okay. First, we're going to look at this tree diagram, and this will enable us to determine how many possibilities something can happen. So if we have 3 rows from Albany to Baker and 2 rows to Baker's to Crestwich, how many ways are there to travel from Albany to Crestwich? So you can see here that from Albany, we have 3 different ways to go to Baker. From Baker, we have 2 different ways to go to Crestwich. So basically here, we have 6 different total possibilities that we can go from Albany to Crestwich. What this is called is basically the fundamental principle of counting. Now, this is only applicable if your events are independent. So first, let's talk about what does 2 independent event means. And we'll look at some more vocabs as well, because you may not understand what is an event. So an event is basically something that occurred. So let me give you a simple example first. So an example of an event is like flipping a coin. Okay? And the outcome of that flipping a coin is head or tail. We call this the sample space. So the sample space is the total of possibilities, or all total possibility. It's all possible outcome. All right, so I'll do another example here. So rolling a die. So a die has 6 faces. So therefore, on each of those faces, we have 1, 2, 3, 4, 5, 6. So this would be our sample space. Okay, so we have 6 different possibilities. When you roll a die, you're gonna get one of these. Okay. So let's look at how we can use the fundamental principle of counting. So this looks pretty confusing for you to understand, but let me give you an easier example of this. Okay, so let's say we have a deal for breakfast, lunch, and dinner. So let's say for breakfast, we have 5 different items to choose from. For lunch, we have 8 different items. And for dinner, we have 10 different items to choose from. So basically, from these choices, how many different possibilities are there for us to pick one item from each, right? So if you think about the tree diagram, here's the breakfast. So you can have 5 different breakfasts, and then from there you stem 8, and from there you stem 10 more. Okay, so the quick way of doing this is all you have to do is multiply all of the individual choices. That will give you your total number of the sample space. Okay, so 8 times 5 is what? 40. Times 10 give you 400. So that means that there are 400 different combinations that you can make so that you have a breakfast, a lunch, and a dinner. Okay, so that is what the counting theory is. So the M1 here is basically how many ways for the first one to occur, M2 how many second ways, M3 the third way. So you just multiply all of them together. Okay. All right, so here, let's look at this similar example here. A restaurant offers a choice of 3 salads. So we have 3 salads, 5 main dishes, and 2 desserts. Count the number of 3-course meals that can be selected. So I have to pick a salad, a main dish, and a dessert. Okay, so we just have to multiply this through, and that will give me 30. Aim, you okay? You have a problem with joining?
Yeah, I'm having a problem with joining the whiteboard, so I'm not sure what's going on here, sir. It says I have a loading error, and I've been trying to join multiple times.
Yeah, I see that. If you can't join, you can just look on the Blackboard page.
Okay, thank you.
Okay, a teacher has 5 different books that she wishes to arrange in a row. How many different arrangements are possible? So anytime that you are looking at problems that deals with arrangement, here's how I suggest you do it. So we want to look at how many things are being arranged and how many slots we have. Okay, so the slots is the one that we're going to draw out here with just an underscore. So we have 5 different books, 5 different slots to put in. So the first slot have how many choices? So ask yourself, how many books can go in each slot? Okay, so you can't reuse the book again, right? So in the first slot here, you have 5 different choices of books to put in. So after that, that book is already there, so you have 1 less choice. So now you only have 4 more books to put here, 3 more books, 2 more, and then the last one, you don't really have a choice because you only have 1 more book. So therefore, we use the counting principle to multiply all of these together, and that will give you your total number of choices or the sample space that you can arrange this book. All right, so what we get here is 120. Okay, now there's a quick way of writing this. We call this factorial. So this is 5 factorial. Okay, so let me define factorial if you haven't seen before. Factorial is a way to write large numbers, and it goes like this. So if you have, for example, 5 factorial, you start with that number, and you multiply each number and decrease it by 1 until you get to 1. So 4 factorial would mean 4 times 3 times 2 times 1, 3 factorial, and so forth. 1 factorial is just 1. Now here's another interesting fact, that 0 factorial is actually not 0. 0 factorial is actually 1. And we need this to be true so that we can deal with combination and permutations. So n factorial is equals to n times n minus 1, n minus 2, n minus 3. So we just keep decreasing it until we get to 1. Okay. All right, so let's look at how this is different from the last example. Suppose the teacher in the previous example wishes to place only 3 of the 5 books in a row. How many arrangements of 3 books are possible? So now we only have 3 slots and we have 5 books. Okay, so you have 5 different choices of books to put in the first slot, and then after that one you only have 4 more books. After that you have 3 more books to put in the last slot. Now we can multiply this. So we get 60 choices. Okay.
Hey, Professor, is this a permutation?
Yes, it is. Very good.
And what's the difference between a permutation and a combination?
We will get to that. No worries. All right, so this is factorial, like I just explained earlier. All right, so let's look at permutation first, then we'll look at combination, and then how do we determine and distinguish the difference between the two. So a permutation of n elements taken r at a time is one of the arrangement of r elements from a set of n elements. Well, that sounds very confusing, right? So let me restate all this here. So in a permutation, the order of the arrangement is unique. So that means it matters if it's in a an order or not. Okay. All right. So the notation that we're going to use is this one. This is the one I like. Okay. But I think the book also used this here. Okay, so we have P. The P here stands for permutation. The N is the total number of objects or elements. And then the R value is the number of objects used. For example, in the last example here, suppose that the teacher in the previous example wishes to place only 3 books. So this would be my R, the 5 would be my N, because N is the total number of books that she has, and R is the number of books that she uses. Okay, and I just explained that here. So let's look at the formula for it. The formula for it is n factorial divided by n minus r factorial. So before we get here, let me help you simplifying factorial. Okay, so let's say I have 16 factorial over 13 factorial times 3 factorial. So if I want to simplify this, you know that 16 factorial means 16 times 15 times 14 times 13 times 12 times 11 times all the way down to 1. 13 factorial means 13 times 12 times 11 times all the way down to 1. So you can see here that a lot of this stuff cancel, right? And don't forget our 3 factorial here. So what happens is that when you are expanding something and you see there are other factorials in the numerator or denominator so that you can cancel, you should try to do that rather than expanding everything out. Okay, so instead of doing it like this is what I would suggest. You expand the largest factorial until you can cancel. So what I mean by that, so 16 factorial here, it can be canceled with 13 factorial. So I'm only going to expand my largest number. In this example, it is 16. And I'm going to stop at 13 because now I can cancel the 13 factorial. 3 factorial I can expand, and this time I can simplify with something in the numerator. So 3 and 15 can go by 3, 16 and 2 can go by 8. So now my answer is 8 times 5 times 14. Okay? Okay, let's see what that is equal to. 560. Any questions?
I saw a notation once where when they were doing, and I can't figure out whether it was the permutation or combination, but it basically wrote it in a vertical column with parentheses. Is that a
Yes,
combination?
that's a combination. Like
Okay,
and
but
like
permutation does not have that kind of notation?
no.
Okay.
We use this for the next section. Okay, so you're going to see this when we do binomial expansions. So that's what they use that for.
Okay.
Okay, so the number of permutation of the letter L, M, and N. Now you can use the formula, right? So NPR, okay, or just think about it like this. You have 3 spaces, and you want to put L, M, and N in there. So you have 3, 2, 1, and that's it. You get 6. Okay, or you can use 3, choose 3. So we do n factorial over n minus r factorial. N here is 3, n minus r, so 3 minus 3, that is 0. So this is the reason why we need 0 factorial to be 1. Because 3 factorial is 3 times 2 times 1, which is 6. 6 over 1 is 6. And that is the reason why we need 0 factorial to equals to 1. Okay. All right, the number of permutation of 2 of the 3 letters L, M, and N. All right, well, again, we have 3 letters, but this time it's only 2 spaces. So we have 3 here and 2 here, which is still 6. So if you did NPR is equals to 3, choose 2. So let's see what we get here. 3 factorial over 3 minus 2 factorial equals 3 factorial over 1 factorial, which is still 6. Any question here? Okay. And you can see here, 3 choose 3 would be 6, and 3 choose 2 is still 6. All right, suppose that 8 people enters an event in a swim meet. In how many ways could the gold, silver, and bronze prizes be awarded? I'll give you some time to try that. Let me know you need help. You can just type the answer in the chat. Mara, do you have an answer yet? Okay, very good. 336 ways. All right, try this one. Any problems on this one? This is actually easier. Try drawing the slots. So how many slots would we have?
We would have 5 slots.
Right, so how many numbers can go in each slot?
The first slot will have 5 numbers, second, 4, third, 3, last, second to last 2, and the last one is 1. So it's 5 factorial.
Exactly. So what's 5 factorial?
Let's see, 20, 60, 120.
That's right. All right, so now we talk about combination. So the main difference between combination here is that the order does not matter. So a subset of items selected without regards to order. Okay. So in the previous examples, we look at whether you have the gold, silver, and bronze. So all of those have different have different level. So that means that they are different, right? Now, if I were to select people to be on a basketball team, everybody is on the same level, okay? So therefore, we are going to use a combination anytime that we deal with the order that we select things doesn't matter. Because if I select 7 people and all 7 people are on the same level because they all have the same job, they're all players, okay? So that means that it doesn't really matter the order that I choose them. After I choose them, they will still belong in the same team or same group. So there's no order between them. So the only thing that's different is this here, r factorial. So the permutation was n factorial over n minus r factorial. The combination, we just get rid of the number of choices that could repeat. Then we use r factorial in order to divide that out. All right, go ahead and try this one here. Okay, you got 48. Oh, that's not correct. 50. How did you get 48? Yes, very good. All right. So I have 8 factorials over 5 factorials and 3 factorials. Now remember that when we are selecting people in a committee, just like a basketball team, everybody is on the same level. So there's no order, okay? So therefore, we use the extra r factorial here to make sure that that number of choices is smaller. Now you can also use the graphing calculator for this, but I don't think it's really required.
Professor, can you check my arithmetic? I know I got the answer wrong. I know that the 5 factorial cancels out, but what happens to the, should I write down the 3 factorial in the denominator as 3 times 2 times 1 and then cancel or
Yeah.
reduce down the numerator?
Yeah.
Okay, so that's,
Because you only have 3. If you have an odd number of factorials, you can't really cancel anything. So just write that.
okay.
If you write it as a product, then you can cancel all you want. All right, look at the next example. Are we done?
I keep getting my answers wrong.
Uh-oh.
Okay, so I mean, like I wrote out 30 factorial over 30 minus 3 factorial times 3 factorial. And on the numerator, I got 30 times 29 times 28 times 27 factorial. On the denominator, I got 27 factorial times 3 factorial. I factor out the 27 factorials out from the top and bottom. So I have 30 times 29 times 28 over 3 factorial. And then I try to simplify the 3 factorial to simplify the 30. So I got 3 times 2 times 1, and then I reduced the 30 down to 10. So on the denominator, I got 1 times 2 times 1, so that's 2. But that gives me the wrong answer of 2940. And I think it's the same kind of mistake that I did on the last problem too. So I'm trying to figure out why I'm doing this, why I keep on repeating this mistake.
Okay. So let me write it out for you. Okay, so here I can cancel this 3 with the 30, so I got 10 here. This 2 with the 28, that's 14. So all I have to do is take 10 times 29 times 14. And I got 4060.
Times 29 times 14. So let's see, that's 10. So I did not cancel out the 2. If I didn't cancel out the 2, that'd still be 28. 10 times 28 times 29 divided by 2. Okay, I see what I did wrong.
So you probably didn't put parentheses around here if you're going to multiply the denominator first. That's the very common mistake. Okay. Okay, so for the part B, in how many ways can a group of 3 be selected if one particular lawyer from 30 has been pre-selected to work on the project? So that means that out of 30, we already selected one that has to be from the group. So that means we only have 29 lawyers left, and then we only have to pick 2 more. So here we have to select 2 from the 29. So therefore, that means we have only 406 ways to do that. Okay? Does that make sense?
Yes.
Okay. All right, so here's the difference between the two. Permutation, the order is important, whereas combination, the order is not important. Now, the formula is almost the same, except that combination, you're going to have fewer number of choices, because here you are dividing by a larger denominator. Okay, so note. Combination will have fewer choices for the same R, N, and R. Okay?
Oh, yeah. Okay. So to put it in other words, permutation, they're all independent events, while combination is dependent, right? I know we're not supposed to get into statistics or anything, but that's the way that I was like hammered into remembering this.
I don't know that that's not true.
Okay.
Because no, that's not true at all. Because you're talking about two different things. When we're talking about an event, and you talk about multiple events, that's why you can talk about independent or dependent.
Okay.
Here, the combination or the permutation tells you how many different choices you can select from that one individual event only. So, for
Okay.
example, okay, so for example, let's say I want to select a committee, right? So let's say select 3 people out of 30 for a committee. Okay, so let's say I have 2 different committees. That means that I have 2 events. Okay, so let's say the first committee, there's 3 people, right, out of 30. The second committee, let's say there's 5 people out of 30. Now the independent and dependent comes in from, are you allowed to serve on more than one committee, right? So if I select somebody for this committee, that means that they have to sit out for the second committee, which means that it's going to change out the total. So that is going to change out the probability. So when you talk about independent and dependent, you're talking about changing the probability or the total number of choices, so that is going to change the probability in the end. So let me give you a more concrete example than this here. This may still look a little bit confusing. So are you familiar with playing cards?
Yeah, sure. 52 card deck.
Right, 52 cards, right? So let's say, what is the probability of picking a king, okay, and then queen without replacement? Okay, so what does that mean? So the probability that I'm going to pick a king in the first card would be 4 out of 52, right? Now, assuming that I got the king correct, and then that means, and I'm going to not replace it back, that means I only have 51 cards left over, and I still have 4 queen, so therefore I have 4 out of 51. This here is a dependent event, because the outcome of the second event depends on the outcome of the first event. So here we are reducing the total number of cards. That's why it's called a dependent event. So dependent
Okay.
means you're manipulating or you're changing the total number of outcomes somehow.
So going back to that lawyer problem, right, where you were trying to find the combination of three lawyers, but then the secondary question was one lawyer has been picked already, therefore you only have 29 lawyers. Isn't that
Yes.
a dependent because that first lawyer has been picked already and he wasn't replaced?
Yes.
Okay, so in this specific example, I guess that's where I was making the connection to the dependent events. But I can see why you say that they are in our lesson. It's exclusive of each other.
Well, here for this lawyer, the first one, you'd have no free choice of picking which lawyer. That's the thing.
Hmm.
Right here, they already pick one for you, right? They say if one particular lawyer has been pre-selected. So this is a different one. It's a different type of probability here. This is called conditional probability. So this is now you're putting probability with statistics in here. So don't
Got
want to
it. Okay.
confuse a lot of people. Yeah.
Sorry, Professor. Just
No, no problem.
curious.
Yeah, yeah, I know. All right, so here's the fun part here. Trying to guess passwords and stuff. So I'll give you a minute to try these problems here. And write the answers in the chat. Let me know if you have any questions or don't understand the question.
Hey, Professor.
Yes. Uh-huh.
On number C, right? Because the teams can't play each other again, that means that the order matters, right?
Each team plays every other team exactly once. Okay, so let's say we have team A, B, C, D, E. If team A play with team C and team C play with team A, is that two different games or one?
That's the same game,
That's the same game,
right?
exactly.
Okay.
So does the order matter?
No, it does not.
Ah.
Got it. Okay, I see what you mean. Okay, but then I'm confused for C again as to how do we determine R here based on just the word problem.
Okay, so how many teams can play with each other at one time?
Oh, it's two teams. Okay, I
Yeah.
see. How many games that each team plays? Okay, okay, I see what I'm doing now.
Maya, are you getting the same answers for A to C? Okay, so can you tell me why you got 9, 10 for part B?
Oh. Okay, how many different are possible?
What did you do for part B? So part A is right. It's 50-40.
What did I do? Let's see.
Are you
50,
talking? I can't hear you.
yeah, I'm talking. Give me 1 second. I'm
Uh,
just muttering right now. Okay, so I had um oh, did I do this wrong? So I chose to do combinatorics here. So NCR, where 15 factorial over 15 minus 3 factorial times 3 factorial. I reduced down to 15 times 14 times 13 times 12 factorial over 3 factorial times 12 yeah, 3 factorial times 12 factorial. I factored out the 12 factorial. I factored out the 3 factorial and the 5 and the 15 up on the numerator. So I got 5 times 14 times 13 over 1. Let me do the math again. 14 times 13. That's how I got 910.
Okay, so what I think you're doing is you did not put parentheses around the denominator.
Okay. So, well, 15 minus 3 factorial times 3 factorial. Okay, and then from there. I'm not sure like where the parentheses would go after I do the arithmetic down in the denominator though.
Okay, so you should have 15 factorial over 12 factorial, 3 factorial, right?
Mm-hmm.
All right. So 15, 14, 13, 12 factorial, stop there, cancel with that. 3, 2, 1. So the 3 here cancel with the 15 gives you 5. The 2 here
Got
cancel with
it.
the 14 gives you 7. So you would multiply these three numbers together.
Oh, I
Now,
see. Okay, so I think I see what you mean now. I didn't expand the 3 factorial. I just canceled it out, and that's wrong because there's no factorial on the
exactly.
numerator to cancel it out.
Yeah, so where did you cancel the 3 factorial with?
I canceled it with 15, but once again, as I stated,
Yeah,
I know now that there's no factorial on the top. So
right.
mathematically, that makes no sense.
Yeah. So remember that factorial is a function. Okay, so you can only cancel if it's the same function. So right here, 12 factorial over 12 factorial is 1. That's why you can cancel that.
Got it.
That's why you cannot cancel 15 factorial with 12 factorial and just reduce that. That's not a number, that's a function.
Got
Okay,
it.
so
Okay.
you can also use a calculator, or you can use ClassCalc in order to do this. Using the, let me see if I can find ClassCalc, the function for it. And you can just type this in without having to go through a lot of pain here.
Yeah, I wasn't able to find the factorial button on my TI-84 easily. It's been a while, but I know it's in the math function.
Yeah.
Yeah. So let's try
All right, so here
15.
I'm going to show you using ClassCalc. Okay, so you're going to hit stats right here. And then over here, you have NCR and NPR. So I use NCR. Now you just have to type in the N and the R values. So the N was 15. And then the R value was 3. And so you should have 455. Okay? That's good?
Cool.
Okay. All right, so part D, all you have to do is take, you have 2 slots, right? And you're gonna use 8 for the first one and 7 in the second one, since you have 2 teams play with each other, but this only play exactly 1, so that's combination. So you have 8 teams, you choose 2, so you have 8 factorial over 6 factorial, 2 factorial. So 8 times 7 divided by 2. So 56 divided by 2, and I think you got 48, no, 28.
Hey, Professor, can we go back to B? I did it on intuition that B was a combination, but as I'm reading it over and over again now, right, I can't define why I chose it as a combination over permutation. Can you help me out with that?
Sure. Now, if you are selecting 3 light bulbs, all 3 light bulbs have the same level, are on the same level. They're not different level. So it doesn't matter if you choose light bulb 1, 2, 3 first, or if you choose light bulb 3, 2, 1, or 3, 1, 2. It doesn't matter. All these are the same group of 3.
Got it. Okay, thank you so much.
Yeah. All right, part D, in how many ways can 4 stockbrokers be assigned to 6 offices so that each broker has a private office? So here, as long as they're inside an office, it doesn't matter who's in what. So the order here doesn't matter. So you have 6 office total. We're going to choose 4 of them. So 6 choose 4. So 6 factorial over 4 factorial, 2 factorial. So we have 6 times 5 times 4 factorial over 4 factorial, 2 times 1. So we get 15 choices.
And I have a question about this one. In doing combinations and permutations, will n always be the largest number, in this case 6?
Exactly. N will
Okay.
always be the larger number or equal to R, but R can never be larger.
Thank you.
And I think this is our last page. Oh, no. Yeah, it is last page. This is just an explanation. All right, so we'll work on 8.5, which will be our last sections. Please work on the homework right away so you don't forget how to do this. It's not that difficult. It's just 2 formula. It's fairly easy to remember. Do you have any question, Amy?
Professor, is there going to be a test review for this upcoming exam next time?
I think there should be. Let me look.
We have the review form, but I know that we're going over another lecture next time as well too. And I know that the test is this weekend, so I was wondering how you would like to fit in the test review in the next lecture.
Let me see.
And I was wondering whether you updated the review form to reflect the extra content that we're doing this semester, because I know that you said that we are learning more than
Yes.
your previous sessions.
Yes. So the next lecture won't be that long, so we can do the lecture and the review at the same time.
Okay, awesome. And just to confirm, is the exam 4 review sheet updated now, or is that something that we need to wait on?
Yes, it should be updated now.
Awesome.
I would have to check right now.
Thank you. And then just to confirm, for this exam 4, how much time will we have? How many questions will there be? And is there going to be a graphing or written portion that we have to submit?
Okay, so let me take each one. So what was the normal length? Was it 2 or 2.5 hours?
It was, the first one was 2.5, but then the subsequent ones you gave us 3 hours total now. Right? I think that was the issue with the last one where we had a reduced amount of time. So it's 3 hours total has been the norm now, sir.
Okay, so that's fine. I'll leave it at 3 hours. So yes, 3 hours, probably around still 30 questions. There will be a graphing portion where you will have to graph a conic sections. Let's see. Yeah, and I think that covers all your questions, right?
Yes, sir. And then for the graphing and the conic section, right? Like I know that you emphasize us, at least for hyperbolas, to understand how the box works to define the asymptotes. When we're graphing for conics, though, do we need to be cognizant about its eccentricities if we're graphing it for this test?
No, you will not be asked for eccentricity for when you graph. Just basically at the minimum 5 reference points of the conic sections.
Okay, thank you. And then just to reiterate, because I was reviewing your second lecture about the conic section, I think it was 8.3, one of those days that I was absent. Can you help me define A, B, and C again when we're looking at conics? I think A, to my recollection, A was the distance from the center of the conic to the vertex. C is from the center to the foci, and then B is from the center to the other axis's edge.
Yeah.
Cool. Yeah, I was just getting confused during today's review. All right.
Okay, so there is some stuff right here that I need to take out. 8.4, I believe. I left out the parametric equations, so.
Got it. Yeah, I was just getting to that because I wasn't familiar with that. Okay.
Yeah, 8.4 will be left out. Yeah, I will update that now. Thanks.
And then we'll do the binomial expansion in the next lecture?
Yes.
Part term. Okay, awesome, awesome, awesome. Any hints on how to like refine or basically how to hammer down our review for the finals? I'm going over the old tests, I'm going over the old homeworks, and I'm just like going over the videos. But going over the videos is really time intensive.
Yeah, I
Would it
would
just
not
be
suggest that. I would suggest do as many examples as you can,
okay?
especially if you want to go. I would suggest you go back and do all of the tests, like the old tests.
Sure, sure. And if
Yeah.
we go over the old tests, right? In your experience as a professor, those who get the best scores, are they the ones who review the questions that they got wrong on the test, or are they the ones who review the questions that they got right on the test and just hammer down those fundamentals?
Um, of course, review the ones that you got wrong, but then at the same time, don't forget the fundamental because that
Yeah, yeah.
doesn't really help. That is it.
Got it. I understand. And before we take the final, right? I know that in the past you mentioned just due to how the performance of all the tests were this semester, you said that you might be giving a curve on all of our tests. Can you reflect that curve on our score before we take the final so we know
Yes.
how to properly gauge our needed
Yeah, I'll
performance on
do
the
that right
finals? Awesome. Thank you, sir. That's just
now. Mhm.
gives us more data and to work with, I guess.
Yeah.
Okay, that's it for me today. Thank you, Professor. I appreciate it.
Great. Yeah. Have a great day. I'll see you next time.
Thanks. Bye.